All right, so thank you so much for the opportunities for me to present my work today. And today I want to talk about my PhD research. So let's start it. All right, so you can see that is a lot of fish and all of that happened. It's not only recently, but it in a span from 1960s and even until now, and not only 10,000, but almost 100,000 feet killed during that time. And all of them, it happened on the south of the Darlings Murray River. So what caused the killings? It turned out that during all of that period, in several reports saying that there is an event of algae blooming happenings, and so people find out that is it because of the changing in temperature, so it changed in the temperature fluctuation, and also combined with the poor management of the river lead to kind of an insufficient river flow that lead to something is called thermostratification, or stratification happen in river. So that it will lower the mixing and lower the oxygen, and it kills the fish. And you can see in all the dramatic photo there, but it's not that just it. So thermostratification also leads to cyanobacterial blooms, and it leads to poison or the reduction of water qualities. So it leads to animal poisonings and human poisonings. So that's why it is really important to learn what caused it and what affect or what change thermostratification in riverine environment. So that is why it led to the motivation of my research. So the title is an investigation of the effects of Meanders on thermally stratified riverine flows. So hello everyone, my name is Duy, and I am from the Sydney Fluid Dynamic Research Group from University of Sydney. And here you can see in the photo here, this is the section of the Murray-Darling River, and you see the color of the green. This is it one section of the bend of the river, and the green river indicate it the algae in the water. So before going further into my talk, I want to acknowledge some of my co-authors. First is my supervisor, Professor Michael Kirkpatrick, and then Professor Stephen Amfield and Nicholas Williamson. So three of them is from the University of Sydney. And the last one, Professor Wensin Lind, he from James Cook University. With their help, with their support to help me to finish all of my work during my PhD. So talk about thermostratification. It happened when a body of water receives radiation from the sun, and with the low flow rate, it leads to a persistence of less turbulent level and mixing, and it leads to the layering because of the density of the water actually changing with the depth or changing with the temperature. So this layering happening, for example, here you can see a 3-layer here. This happen, it will suppress the turbulent and mixing, and it change the flow characteristics, and so that why it lead to a really suitable condition for algae blooming, or in other hand it lead to the fish kill that I talked earlier. And there is locally that there is 4 group of factors actually influence the thermostratification. The first one is atmospheric condition. For example, you have some of the rain, you have the solar level, or you have the wind mixing the water in the first layer here. So it all change the shear stress or the turbulent kinetic energies. And the stream bed is also for the conduction or the groundwater input. It all of them change the the energy, kinetic energy associated with the bed. And of course, we also change the flow rate or turbulent river or the stream discharge. But I want to focus on the topographic condition. So in topographic condition, it maybe about how thick is the trees around the river. So of course, it blocks the sunlight. But it also talking about the river side or the river shape and size. And one of the interesting feature of river is a meandering section. So of course, river have, like you see in the bottom right here, river include a lot of meandering sections. And so for modeling a temperature in river is already complicated enough. But if now we include that there is water flowing through a band, so there is more of the physical aspect that associates with water flow through a band, as you can see here. Because we have a strong activity of the secondary flows, so it leads to the creation of some of the cell, so the central cell or the outer bank cell here. So those kind of cell, it make the topic that we investigate here is more interesting, because this cell actually changing the characteristics of the mean flow and the turbulent flow in a river. So it will lead to the change of the stratification. So let's find out how it do that. So first we need to model a river. So to do that, so here is the section of a kind of the real river, where you have the uneven bed, you have that the meandering river here. And to model that, we use a size generated curve function, as you see in the equation here, and that will lead us to a meandering curve as you look in this photo here. And to idealize it or simplify it, we also make the cross section is rectangle. And then when we have this, we change the curvature. So here I just see it stands for curvature in the range of curvature from very mild to a very sharp meander. And we also change the sinuosity. So we change that by changing the theta zero here. It calls the deflection angle. So when we change that, we actually change how sinus is it of the river. So it also have the range from not very sinus to very sinus manner, and all of this range curvature or sinuosities actually reflect a range of the nature river from various reports in literature. So once we have that, we need a governing equation. So it is a bunch of mass, momentum, and energy conservation equation. So Navier-Stokes equation. And here we also have a heat sort Q here. So this heat sort is actually following the Beer-Lambert law. For boundary condition, we have the no slip adiabatic wall for the side wall and the bottom. So it have the wall there, and on the top we have a stress-free adiabatic for the top. We also to make it more to save the computational cost, we want to mimic only half of the meander. So instead of modeling all of the from 0 to 2 here, we could just do it from 1 to 0. And to do this, we use an anti-symmetric periodic boundary condition for the inlet and outlet. So it's the same as the periodic boundary condition, but it actually mirrors the cross stream direction. So here an example here, you can see that all the things that come out from the outlet and go into the inlet here. So from the outer bank, it mimic mirror cross section and it go to the inlet, to the inner bank here. So this is the anti-symmetric periodic boundary condition. So when we set that, we let it run for a while when we get statistically condition, and then we collect the data. We collect it for 30 to 40 time unit, so it's enough for us to actually have get the converse of the time average. And to do collecting the data, of course, we will not collect it for all of the self, and this kind also a kind of the smart setting as well. So we collect it on probe stencil. It means that instead of all, like for example, this case is almost 200 million cells, we collected on it different of the each of the unit. You can see it is the example of the grid on the probe stencil that we collected here. And when we're doing that, so all of the probe that we collect in here to enable to calculation of the spatial gradient. So each of the probe actually measure the data of the horizontal stencil, not only on the probe, but also on the neighboring nodes as well. So you can see it in some of the writing in here. Okay, so now we have the setting and the model and the equation. We run it and got the data and analyze it. I will talk about the results that I have. So the first one is published in Physical Fluid 2021 when we compare in a very sharp manner between a stratified flow and a neutral flows. So for stratified flows, we turn on the buoyancy coefficient lambda, it equals 0.5. And for neutral flow, we turn it off, so lambda is 0. And you can see it is the contour of temperature and vorticity and streamwise velocity, and here is the vertical vorticity. So you see that there is some fundamentally different between a neutral manner and a streamwise, a stratified flow in the manner here. The first thing is you have see that there is two V1 and V2 is the separated shear layer. This shear layer happens because of the high fluid in going to the inlet, and it deflect out to the outer bank here. But the difference is that in a neutral flows, because of the water, it more mixing, so that why this high stream wide fluid actually not slide quickly to the out from inner to outer bank, but it go cleaning along the center lines, and it go not until really further after the banner plate to get to the outer bank wall. However, in the stratified flow, it actually quickly slide into the outer bank wall, and that created adverse pressure gradient for the region after the banner plate here, and that created another separate shear layer here. So when we have another separate shear layer here, it actually go out of the outlet and again it got picked up in the inlet here by our anti-symmetric periodic boundary condition, and that two separate shear layers actually met before the outlet here, and it amplifies the turbulence here. So you can see that the turbulent amplification is a well-known phenomenon for flow through a concave wall, but for stratified flow, we see that it is more amplified in stratified flow compared to neutral flows, and the reason is because of the two separated shear layers that I just talked earlier. So that is for a very sharp manner. So what happened if now we go into changing the curvature? So when here is the one that when I change and vary the curvature from a straight flow, a straight channel, and it increased curvature. So this one also come from a recent published paper in Physics of Fluids, and here we also see just several things. The first thing we can see is the change of the deflection location. So you can see that it actually get earlier to the entrance if you decrease the curvature. So go into this direction. So this one is almost to the bend apex, and then it go earlier to the inlet here. The second thing that we could see is the changing in the level of stratification. So you can see that here is the plot of temperature, and here you see that it is more stratified. So you see the two distinct layers of temperature here, but if you can see that the temperature is almost mixed out here in the high curvature case. And we also try to validate it by using some of the analysis through the first thing is we look at the kinetic energies, and we also look at the strength of secondary flows, and both of them actually increase with the increase of curvature here. So this it indicates the degree of stratification. And we also look at some of the friction and bulk reduction number. Here is interesting that we see there is an increase of the both bulk and friction reduction number from the straight channel to a lowest curvature, but one is go to a curved channel. One in that when you increase the curved channel, it actually decrease both of the reduction number, as you can see in here. So it tells us is that in a really low curvature case, the stratification level actually higher than in the straight channel case, but when it go into the meandering channel, so you increase that for increase the curvature, you actually decrease the stratification. And we also look at the analysis of the potential energy buckets. So here is a plot of available potential energies, the background potential energy and the total potential energies. So here, for example, if I look at again the curvature, if I look at the total potential energies, I see the same trends as it in the bulk reduction number. So if the magnitude of the total potential energies decrease from the straight case to the lowest curvature case, but then after that it increase from the lowest curvature case to the as we increase the curvature. So JIT finding actually also have some similar finding in the estuary flow in the literature, but in the estuary flow, they only compare between the straight channel and another curved channel. But here we actually have a symptomatic range of curvature, so that's why we could see the trend between not only the straight channel to the lower curvature case, but we also see the change of the level of stratification between all of the higher curvature case. All right, so that is when we change the curvature. So now, how is it look like when we change the sinuosities? So this one is actually submitted to the Journal of Hydraulic Engineering when I change the sinuosities. So this, you can see that sinuosity increased from 1.07 to 3.7 here. And I also compare between lambda is 0.5, so it's stratified case, and lambda is 0, so this one is neutral case. There is some different thing that I could tell from all the plots. So here the plots here is again did it streamwise velocity and did it temperature. The first thing is I see there is the difference between the changing in the separated shear layer. So here I have only V1, so only one separate shear layer for lower sinuosities. But then when I come into a higher sinuosity, I have two separate shear layer, and you can see that this one will actually change the characteristics of turbulence. So whether it will amplify the turbulent intensities in the river. And when I also want to see that there is also changing in something I call it the low streamwise velocity zones or the separation zone in the river, and I see that there is a change of that zone here. So if I plot the length of that separation zone, I see there is a decreasing of that zone when I increase the sinuosity here. And there is also that there is, if I compare between stratified and neutral flow, then the length for that zone for neutral flow is higher than the one in stratified flow. The reason is because in stratified channel, there is a gliding between layering of the water level of the water layer that lift all of the one that changing of the high streamwise velocity actually glide to the outer bank, the same in the sub-meander that I talked earlier. And it's the same in neutral flow, but here because we have more mixing, so that gliding thing not happen until fall to the end to the outlet of the channel. So that left us with the changing of the length of the separation zone here. And of course, when we look at the temperature, we also see a range of temperature is also different. So when we increase sinuosity, we see a more stratified flows. It's because of the change of that. It's also associated with the change of the mixing. So you see that the temperature here is more distinct or more stratified when I increase sinuosity. So because of the changing in separation zone or the changing in the activity of secondary flow, and then I want to look how it changed the shear stress in my channel. So if I look at the bed shear stress, I also see some changing here. You can see that there is a change in bed shear stress. For example, I plot out the range of my bed shear stress, and it actually, when I increase sinuosity, it increases the bed shear stress. I also see that there is also a lower of the bed shear stress in the neutral channel here. And I validate that by plotting out something it called turbulent anisotropies. So this is plot of turbulent anisotropy in the right here. And I also plot the range of turbulent anisotropy here. And you can see that it's pretty consistent with the trend of the bed shear stress. So this could actually lead us to saying that when I increase the sinuosity, I actually increase the range of bed shear stress. And of course, this is associated with the activity of the secondary flow. To more detail, it is the activity of the central bank cell, and that central cell actually help the flow when it go into the wall here. You can see that when it go to the wall, it go down to the bottom. When it go down to the bottom, it change the bed shear stress in the bottom, and then it also go into the bed. When it pick up the momentum, then it go back to the top. And that activity of the central cell changing the bed shear stress. It also changed the wall shear stress. So this is the plot. The two in the right here is the wall shear stress. This is the inner bank. So A is inner bank and B is the outer bank. In the inner bank, I see that there is when I increase my sinuosities, it decrease the changing, it decreases wall shear stress in the inner banks, and also it increase the wall shear stress in the outer bank. So this one could easily explain because, like I say, that because of the gliding out of the deflect out of the high velocity fluid. So when it hit the wall, so it will increase the shear stress in the outer wall, and when it lift or it deflect from the inner bank wall, it actually decrease the shear stress in the inner bank wall. And we also see that compare between neutral case and stratified case, we see that in the neutral case we have less wall shear stress, and that's because we have a delay of the going outward of that flow in the central bank cell. So that it also could explain the reason why we have a lower shear stress in the outer bank wall for the neutral case here. So you can see that coming back to all of the three paper here, the first one with the sharp Meander, second one when I change the curvature, and the last one when I change the sinuosities, we can see that all changing of that geometric parameter, it will influence not only the turbulent activity, turbulent intensity, it also influence the flow characteristic, it influence the temperature profile, and also the shear stress in the channel. So this is actually preliminary, so initial results that we could actually find out that changing of the geometric parameter of a river actually influence the level of stratification. And knowing that, it means that it will help us to build a better model for river management later on. So rivers, it's worth it, especially in a really hot and prone climate like Australia. So I hope that my study will actually help somehow like contribute to a broader of the river management program in the future. So thank you for listening. So that's all for my presentation today, and I'm welcoming for any question.